Hi static engineers, welcome back. Today we will discuss about allowable stress. We will discuss about what is allowable stress and why we are using allowable stress, where we are getting the allowable stress for the material, those kind of things we will discuss. Actually, this topic is very much important to do any calculation in ASME, section 8, section 1, section 4 or section 3, any code. It is very much important. We have to use these allowable stress values to calculate the thickness of the vessel, thickness of anything, any component. So this topic is very much important. Most of the engineer directly go to ASME section 8 and for those ASME section 8 classes, but it is very much important to see another code which is related to ASME section 8. It is not ASME section 8, it is different code. We will discuss about that. In this first slide I have mentioned that why don't we use full material strength. If we have a material, the material strength is 100%, we are not going to use the 100% of the material. We are going to use something here. We are saving the limit. Why? What is the reason we are doing that? That we are going to see in this video. First of all, what is allowable stress? Allowable stress is a permitted stress, the absolute highest stress the code allows in your design. That is the maximum stress which code allows you can able to use for a particular material. Safe working limit ensures the vessel operate comfortably without risk of deformation. We are operating a vessel, we have to be in a safest position, we have to give some cushion for the particular material. That is the allowable stress, and this is not the actual strength of the material. As the previous slide I told, as per this slide, the 100% is the total strength of the material, but we are not going to use the full strength. We limit at some point. Okay, why we are giving this safety and everything, that we will see in the next slide. Engineering is about safety. It's simple. Engineering is always about safety. We have to be safe for ourselves, for other humans working in that particular environment, or if it damages any human life, any other environmental thing, that is not at all acceptable. Engineering has to be in a safest limit, so not the maximum capacity. We can't able to use the material maximum strength. Okay, and controls the limit, we keep operating with highly predictable safe zone. So we have a material, we have already known that this is the safest limit of the material. After that we can't able to assure that this material is going to fail or not, but maybe it can withstand, but maybe it fails. As I already told, our main goal is to protect the human life and the plant asset. That is our primary goal. We have to concentrate on safety, always safety first. If the material has 100% strength, why are we reducing the strength? What is the reason for reducing the strength? In this slide you can able to see that there must be some material defects. Not all the materials are 100% in a perfect stage, right? Manufacturing of material is kind of a art. You can't able to copy the 100% of what the material which produced 1 hour before or previous batch. So all the material has small, very slight different kind of properties. So if there is any material defects, we can avoid that. And welding imperfection, actually it's happened a lot, because if you take a large pressure vessel, complete pressure vessel can't be able to weld it with a single person. There must be 2 or 3 persons who are doing those weldings. Even one person is welding, we can't able to assure what he has welded 1 hour before and what he has welded now. The welder is too human, right? So there must be some welding imperfections in the complete vessel. And temperature effects, normally if you take a atmospheric temperature in our country, in India, it is fine, but if you go to Europe or any other western countries, not western countries, mostly the countries located in the north pole or the south pole, the temperature continuously varies. In the half of the year the temperature will be hot, and in the half of the year it will be freezing cold. So the temperature rises, and in service condition also the temperature may vary. Uncertainty of loading, it is normally happened in every plant, because during a peak time they need highest production, they will give overloading. Actually these things will happen, but it's not officially happen, it's unofficially also it will happen. During that time our vessel has to withstand those loadings, those temperatures, those pressures, everything our vessel has to withstand. So we have to design the material with some safety margin. For the safety margin, we are introducing factor of safety. In this slide we can able to see that we are reducing the actual strength. We divide the breaking point of the steel at specific number. We know what is the breaking point of the particular steel, and we are providing some extra margin and we are dividing the particular part and we are using it as a allowable stress. Okay, introduce safety margin. This creates a buffer zone to handle unexpected pressure spikes or material flaws. So as I already told you about this, during operation if there is any unexpected pressure spike or any material flaws, that time we have to be in the safer side, so we are using the factor of safety. Here you can able to see the allowable stress formula. Allowable stress is equal to actual strength divided by safety factor. What is the actual strength? Actual strength is the ultimate tensile strength, otherwise yield strength. For example, you can able to see here the ultimate tensile strength divided by 3.5. The 3.5 is the safety margin which we are going to provide for ASME section 8 division 1. Are we going to use for all the materials 3.5? That we will see in the next slide. How ASME defines the allowable stress. Actually, this allowable stress is generated using each and every material. Each and every material behaves in a different manner. Some behaves very good for the low temperature, some behaves very good for the high temperature, some behaves very good for the impact test. Those kinds of things are there. We are considering the safety margin using two terms. One is for the yield strength, and another one is ultimate tensile strength. In this graph you can able to see that actually this graph is very familiar to you, I hope, because this graph is from academy. This is a stress and strain curve. For all the material the graph will be little bit similar. There must be some dip or high, but almost all material behaves like this graph. Actually here you can able to see that up to here it is Young's modulus, and here the yield strength happens, and after that the ultimate tensile strength happened. Here the failure will occur. For some material yield stress will govern and some material ultimate tensile stress will govern. For example, for CS material most of the time, almost most of the time, ultimate tensile strength will govern. For the SS material, for the alloy materials, for mostly for high alloy materials like stainless steel materials, the yield strength will govern. In ASME 8 itself, for SA 5 and 6 grade 70, the ultimate tensile stress will govern, and for SA 240, SS 304, the yield strength will govern. Actually, this is a conservative selection. ASME calculates both the margin and uses the lowest value of both ultimate tensile strength and yield strength. Okay. If you want to know the safety margin of a particular material, just divide the ultimate tensile strength with 3.5 and compare with the yield strength, which is divided by 2.5. Whichever is lower, we have to use that as the allowable stress. Okay. And where we can find these allowable stresses? It is mentioned in anywhere? Yes, it is mentioned in ASME section 8 part D. As I told in the introduction of this video, many engineers miss this standard. Actually, this standard is very common for all the standards, all the design standards like ASME section 1, ASME section 8, ASME section 3 and ASME section 4. For all the design sections, this ASME section 2 is pretty common. We have to use this ASME section 2 part D for almost all the vessel design. In ASME section 2 part D, there is list of pages has given for the material tables. In the material tables, you can able to see in one column the material names will be available, and in another column the yield strength, the ultimate tensile strength, those kind of details will be available. And in another page you can able to see the allowable stress for each and every temperature. They have given almost 50 degrees Celsius as the margin, and they have given the allowable stress for each and every temperature. If you want allowable stress for any odd temperature which is not given in the ASME section 2 part D, you can able to interpolate and you can able to find those particular allowable stress. Okay. And why we are using this standard? Why we are using this ASME section 2 part D? To standardize the data, to ensure each and every person in the whole world we are using the same allowable stress which ASME has provided. When we are designing ASME pressure vessel, we have to use the ASME allowable stress. For other codes, other allowable stress might be there. So if you are designing a vessel for ASME, you have to follow the ASME rules. So if you are designing a vessel for ASME section 8 division 1, we have to use the allowable stress from ASME section 2 part D. I already told you the temperature increases, the allowable stress decreases. In this graph you can able to see that I have taken some sample for pipes. This is the CS pipes. Here you can able to see that the yellow color graph is for A106 and the red color graph is for A53. Actually, for a particular temperature until the temperature 400, material strength remains in a straight line. The strength of the material decreases when the temperature increases. For A106, you can able to see that until 400, the material strength remains straight line, and after that the material strength has a steep fall down. That is due to temperature. This one we have already discussed in the previous video, the design temperature video. If you have not watched the design temperature video, please go and watch the video after finishing this video. Okay, and does the allowable stress impact the design? Yes, it will impact the design. It controls the thickness. If the allowable stress is very low, the thickness has to be drastically increased. You have to remember this: the allowable stress decreases, the thickness requirement increases. So it will directly impact on our design. It will influence the cost of the material. If you are going for the thicker material, the cost of the material will be very much impacted. So there will be more impact on the allowable stress. It influences cost, it affects the safety, and it will control the thickness. Okay, we have came to the end of the video. Now I will give you some takeaways from this slide. Allowable stress is safe stress limit. It is not the breaking point. That is our first takeaway. It is pre-calculated and defined by ASME. It is available in ASME section 2 part D. That is the second takeaway. And it is heavily dependent on the temperature. Allowable stress varies for each and every temperature, and it fundamentally controls the vessel design and cost. So while designing a pressure vessel, allowable stress is very much important. So to know about the material, please take the ASME section 2 part D book and turn the pages. You can able to see there are number of tables listed for the allowable stresses. Just verify the allowable stress with yield and ultimate tensile stress. Just compare which one is governing the allowable stress, so that you can able to get a clear picture about the allowable stress. Okay, bye.